All right, so we're going to move into the second part of the course material now. So far, we've been working with circuits that, other than glitches, we can describe their behavior with a truth table. These are called combinational circuits. They're combinational because the behavior of them, the output that they produce, is based on the combination of input values. And if we know what the inputs are, we know what the output is. And we can make, for example, a truth table and then look up a particular combination of inputs and in the output column see exactly what outputs are produced by the circuit. But it's more interesting when we talk about what are called sequential circuits. And sequential circuits depend on more than just the combination of current inputs. They depend on the sequence of inputs, what the inputs have been over time. Perhaps the most recent inputs before the current ones, perhaps the last 5 sets of inputs. So they are circuits that have a memory. They have an ability to change their behavior based on what has happened in the past. And we can learn how to control this memory to get very specific behaviors out based on sequences of events. And these are, what most of the more interesting circuits are that we deal with in digital logic, including things called state machines. And an example of a state machine is, a computer. It's a very, very complex state machine. But a computer absolutely depends on what's happened on the past. For example, if I click my left mouse button, what happens? Well, it depends on what's happened previously. For example, if I move my cursor over a spot on my window where there's a little X in the upper right corner and I click my left mouse button, the window closes. If I move my cursor over a link in a web page and I click my left mouse button, I go to a new web page. If I put my cursor over a file and I click my left mouse button, it opens the file. So we could not make a truth table that said when the left mouse button clicks, here's what happens, right? It depends on the context. It depends on the state of the system. In particular, where the mouse has been placed in the past. So that's an example of sequential behavior. So we need some way to store information in a system so that the system can respond to things that have happened in the past. And the key to doing this is going to be to introduce feedback. So let's start with a simple but pathological circuit, an inverter whose output is connected to the input. And let's ask, what is the output value X? Well, we don't know. It could be a 0, it could be a 1. When you first power up a circuit, it's pretty hard to tell what the voltage is at any point in that circuit unless it's connected to power or ground. Well, the input of this isn't directly connected to power or ground, it's connected to the output. But let's suppose that X is a 0 to begin with. So, that 0 goes around here. Well, since this is an inverter, that 0 is going to change into a 1. X is going to become a 1. That 1 is going to come around to the input of this inverter, and the inverter is going to change it into a 0. And then when we have a 0 coming out on X, that's going to go to the input, and the input of the inverter being a 0 means the output will become a 1, and so X will go high. And so all by itself, X will tend to do this. It will oscillate, go back and forth. Now in practice, if I actually take an inverter and hook this up, this doesn't happen. But if I take 3 inverters and hook them up in a chain, I'll actually get this. It'll be a really sloppy waveform, but it'll oscillate back and forth, and you can see that on an oscilloscope. But if I build a similar circuit, but I use 2 inverters, we've got a very different situation. So what is the value of X here? Well, I don't know, but suppose X is a 0. Well, then I have a 0 coming in here. This inverter outputs a 1 going into an inverter outputs a 0. It's going to stay a 0. So if this output happens to be low, it'll stay low forever. But if this output happens to be high, that 1 will go into the input of this inverter. The inverter changes it to a 0, so 0 goes into this inverter. It outputs a 1. X is going to stay high. So whatever value X is at, it will stay at that value forever. Now, we don't normally want to take the output of a gate and connect it to power or ground. That creates a short circuit, and it, can stress the circuitry inside, and if we do that for long enough, it could damage the chip, right? Not a huge deal, but it's not something we would normally do as part of a good solid design. But, if I were to take a wire connected to ground and just momentarily touch it right here, right? Just even though this chip is trying to put out 5 volts, just tap a wire here that's connected to ground. That will pull this output down to 0. And then when I take that wire away, well, that 0 goes in here, gets inverted to a 1, gets inverted to a 0. This X is going to remain a 0. And if I take a 5 volt rail and I connect a wire to it and I just momentarily touch that 5 volt right here, even though this inverter is trying to put out 0, the 5 volts coming in on a direct wire will be enough to pull this point up to 5 volts, logic 1, and that logic 1 will go into this inverter, come out as a 0, go into this inverter, come out as a 1. And then when I take that wire away, X remains high. So I can take this output and I can run it through an LED and a 1 kilo ohm resistor, and I have a memory circuit. And what it remembers is whether the last time I connected something to this point, it was a connection to ground or a connection to 5 volts. If I just take this 5 volt wire and I tap it, my LED will come on. And, even though I've taken that wire away, the LED will stay on and say, hey, most recently I was connected to 5 volts. But if I take this wire that's connected to ground and I just touch it and let it go, the LED will go off and it will stay off. So that's a memory circuit, right? It can remember the last event that happened to it. Was this point temporarily connected to 5 volts or ground? And it'll turn the LED on to say 5 volts, off to say ground. Okay, that's the basic building block of a memory, but it's not practical because, as I said, we don't actually want to take a circuit that's trying to generate a voltage level and connect a different voltage level to it, right? That creates a short circuit. So we can modify this using, guess what, NOR gates. So let's make a NOR gate and connect its output to another NOR gate and connect this back in. And let's take this output here and call this X. And these are 2 input NOR gates, so I'm going to have a pair of inputs. I'm going to call this input R and I'm going to call this input S. And let's look at what happens with S and R. So suppose S and R are both 0. Well, remember, if we have a NOR gate with a 0 going into one input, that acts like a NOT. It acts like an inverter. So each of these NOR gates is acting like a simple inverter. And whatever value X currently has, when we set S and R both to 0, it holds that value. So X is going to be, X's previous value. All right, now what happens if I leave S at 0, but I set R to a 1? Well, I have a 1 coming into a NOR gate. Remember, 1 going to an OR makes the output 1, so going into a NOR makes the output 0. X is going to become a 0. And it doesn't matter what's coming out here. It doesn't matter what's going in there or going in there. If I have a 1 coming in on this R line, this is going to be a 0. So by hitting this reset line with 5 volts, my output drops to 0. Now if I go back to 0, 0, X will stay a 0 because X always shows its previous value when both of these are 0. But if I were to raise S to 1 while R is 0, well, putting a 1 in S makes this output 0. And if R is still a 0, I have a pair of zeros. The OR gate outputs 0, the NOR outputs 1, X outputs 1. So now I have a nice controlled way of storing a 1 or a 0. If I pull this input to 5 volts and then drop it, my output is a 0. If I pull this input to 5 volts and then drop it, my output is a 1. So I can reset or set the output. And you know, setting an input to 5 volts or ground, that's not a problem. That's what you're supposed to do with inputs. It's different from forcing an output to be high or low. So this is a very simple memory element. And in the case where S and R are both 1, the fact that R is a 1 is enough to force X to a 0. But that's kind of an unusual state. The way we think of this block is it's a device that remembers 1 bit of information, and I can set that bit by raising this line, or reset the bit, clear it by raising that line. And we don't usually think of doing both things at once, which is what this state is. If I happen to do both, the reset clears it. So we call this reset dominant, because the reset line takes precedence over the set line. And so we can draw a picture of this as a different kind of device with an S and an R input and an X output. And this is called an SR latch. So a lot of times when these are drawn, in fact most often when these are drawn, you'll see them written like this. And so this would be our output X, this would be the reset, this would be the set. And you see them drawn one on top of another. So we saw that when we looked at the schematics for the Apollo guidance computer. There are a bunch of pairs of these cross-coupled NOR gates. It's exactly the same circuit as that, just drawn differently. But this is sort of the conventional way of drawing it. All right, so we have an SR latch. It's a device that we can set or reset by either making this line high or making that line high. So that's another building block, but we're going to keep building new devices out of old devices. This is not the most useful way to build a circuit to remember a bit. Because, you know, a lot of times what we have is, hey, here's a bit coming in, please remember that value. But right now we have to say, hey, I've got a 1 I want you to remember, okay, let's raise this line and then drop it. Or I've got a 0 I want you to remember, okay, let's raise this line and drop it. So let's look at the timing behavior of this first, and then let's improve on the design. So timing diagram, here's S, here's R, and they both start off low. And let's suppose X starts off low. So if I raise the set line, as soon as I raise set, X goes high. And then I drop set, and X remains high. And then I raise reset, and at that point, X drops low. And then I drop reset, and X continues to be low. So that's basic timing diagram. Here's why it's a sequential system. Because at this point, S equals 0, R equals 0, X equals 0. At this point, S equals 0, R equals 0, but X is equal to 1. And at this point, S equals 0, R equals 0, X equals 0. So simply knowing the current values of S and R does not tell us what the value of X is. To know the value of X, we need to know that at some point previously, S was a 1 while R was a 0. And that's what made the X become a 1. All right, so let's make a few more embellishments to this design. We have our basic set reset latch. But it would be more useful to have a device that we can simply feed a bit into and say, remember this bit. and it'll ignore that input until we say remember this bit, and then it'll remember it. And we can do that with a little bit of external circuitry. So I'm going to have a data input signal, and I'm going to have a load signal. And if data in is 1 and load is 1, I'm going to hit the set line. And if data in is 0 and load is 1, I'm going to hit the reset line. Alright, so what is this going to do? Right? If my load line is 0, both of these are outputting 0 because they're AND gates, S and R are 0, nothing happens. If the load line is high, exactly one of these is going to output a 1. If D is a 1, this will output a 1, because 1 and 1, and this will output a 0. That sets this latch and the output goes high. If Dn is low, then we have a 0 going into here, so the S input is still 0, but we have a 1 coming into here. 1 and 1 is 1, the reset line is high, the output goes low. So our timing diagram looks something like this. So our load line, our data in can be going up and down and it doesn't make any difference. Let's say our output is low. And then at this point, our load line goes high. At that moment, the output X goes high. And then the load line goes low. And the output X stays high, and changes to data in are ignored until the load line goes high again. And at that point, it looks at data in's low, the output goes low. And then the load line drops. These should all have been lined up, by the way. All right, so this is a little more of a conventional kind of memory element, right? We can say remember the data value, and it remembers it. We can say remember the data value, and it remembers it. So that's an example of what we could call a D latch. And block diagram looks like this. Data in, load, and X comes out. Alright, now there's one problem with this D latch. If our load line is high, and while the load line is high, data in starts changing, guess what happens? Our output changes also. Right? When the load line is low, the output is stable. It ignores what's coming in on the data in. But while the load line is high, it is listening to the data in input, and it's copying it to the circuit's output. And this is going to end up being another version of a glitch. And we'll see why in a few minutes. All right. So refresher, right? We started with this or this. This is an SR latch. It's got a behavior like this. We can use an SR latch, add a bit of additional circuitry, and create a D latch that takes in an input and loads it into this memory unit whenever the load line goes high, and copies that saved value to the output. The downside of this is while the load line is high, the output is matching any changes on the input. Okay, why does that matter? Suppose we're writing a program and we're about to execute the statement x equals x plus 1. So this is a C statement, for example. We have an adder, and it takes two numbers in. Let's put our two numbers in here. We'll call this A and B, and it generates a sum coming out. All right, Well, we can take a bunch of these D latches and we can put them together side by side to make a D register, right? We'd simply have a bunch of these. We tie all of the load lines together, and we'd feed one bit in here, another bit in here, another bit in here, and the outputs would come from the different outputs of each D latch. And we could store, instead of 1 bit, 3 bits, 6 bits, 8 bits, 64 bits, right? So we can make a register. So let's imagine that we have some kind of register. And I'm going to introduce a new piece of notation. When we have an arrow, that means, you know, there's a bit moving from here to here. If we put a slash on it, it means it's what's called a bus. And a bus is just a collection of lines carrying a set of signals that are related to each other. So this could be 2 lines, 8 lines, 64 lines. It's a bunch of lines carrying something like, I don't know, a 32-bit number coming out of this register. So this register could be 32 D latches. And here's the output X, here's the input DN, and here's a load signal. All right, so into the A input, we're going to input the constant 1. So if this is a 32-bit adder, it's going to be 31 ones with a 1 in the least significant bit. And this adder, you know, could be built up from 32 full adders. And what it's going to do is basically take this number and this number, add them together, put the sum out on this set of 32-bit sum outputs. So if this is a register containing the value of some variable x, and this is the constant 1, the output from here will be x plus 1. And our instruction says we want to change x to be equal to 1 more than it is right now. So this is pretty easy to imagine. We just take the output of that adder, we feed it to the data input, and then we say load that new value into x. So if x is equal to 17, we're going to get a 17 in here, a 1 in here. Our adder is going to put out 18. 18 is going to be sitting on the data input of this register. And when we raise the load line, we'll load an 18 into this register, and now x is 18. And that works great, right? Except for one thing. How wide should we make this pulse? Because remember, while that load line is high, the output's going to reflect whatever is coming in on the input. And if we raise this load line for 10 seconds, if we make this a very wide pulse, come up 10 seconds, come back down, what's going to happen? Well, we had an 18 coming in here. The 18 is going to come on the output of this register, get added to a 1, we're going to get a 19. 19 is going to go to the data in. If the load line is still high, x is going to become 19. 19 plus 1 is going to be 20. 20 is going to come around these wires, go to the data input. If the load line is still high, 20 is going to get loaded in there, x is going to be 20. And if we leave this high for too long, instead of x being equal to x plus 1, x might get incremented by 3 or 5 or 10 or 200 or 2,000. But if we make this bus too short, there may not be enough time for this register to actually load in the new value from D in and remember it. Because remember, the circuitry takes time to respond to changes to the inputs. So we have a timing issue. We have a potential for glitches. We have what's called a race condition. Where the behavior of the circuit depends very, very critically on the timing of this load signal, as well as the physical characteristics of these devices, how quickly they respond, which, by the way, depends on things like what the temperature in the room is. And if I do this in a room that's heavily air-conditioned, or I do it in an un-air-conditioned lab in the middle of summer, I'm going to get different behavior out of this. And that's just a nightmare to try to design around. If you have to design a circuit and it can only work at a certain temperature and with certain controls on the voltage going in and certain relative humidity and only with a certain probability, that's just a nightmare. So these are useful building blocks. These D latches are part of a better type of memory element, which is what we actually use, and that's going to be a device called a flip-flop. So let's look at what a flip-flop does. So imagine we have a D latch, load line, data in, and an output. And let's make a pair of these. So here's our data in, here's our output X, here's our data in, here's our output X, here's our load input. And I'm going to take this latch's output, feed that to that latch's data in. This is going to go to the outside world. This is going to come in from the outside world. I'm just going to call this D. I'm going to call this output Q. And I'm going to make a new input that I'm going to call a clock. And I'm going to do something really funny with the clock line. I'm going to take the clock and feed it directly into this load line, but I'm going to run it through an inverter and feed it into this load line. And I'm going to think of this whole thing as a new type of device. This is going to be a D flip-flop. And it basically has a D input, it has a clock input, and it has a Q output. Alright, so let's think through the behavior of this circuit. Suppose my clock is equal to 0. So the clock is low. So this is a 0 coming into this load line. The output's completely stable, right? This latch is ignoring the D input. X is just whatever X is. But if the clock is 0, this load line is high. So whatever the value of D is, that's being copied over to here. That's being set to this data input. But it's only going halfway through this circuit, right? While the clock is 0, whatever's on the data input basically gets this far out onto this line right here. And then when the clock raises from 0 to 1, two things happen. First, this line goes to a 0. So now this starts ignoring its D input, and whatever the current value is here is fixed. But also, since the clock line goes here, this output X now reflects this value coming in. And Q reflects what the value of this D was at the moment that this edge occurred, at the moment that the clock raised from 0 to 1. Alright, at this point, if D starts changing, nothing happens, right? Because our load line here is a 0, changes to D, no effect. Doesn't change the output here, it just goes here and it kind of hits a wall. And then when the clock drops back to a 0, well, now any changes to D are going to appear here, but this load line is 0, so those changes hit a wall right here, and Q is still stable. And nothing changes on the output side until the next positive going edge of the clock. And at that moment, whatever the current value of D is, that gets copied to Q. So the terminology here, a latch is what we call level triggered, meaning the output follows the input depending on the level of this load line, whether it's high or low. A flip-flop is what we call edge triggered, meaning that the output changes only when the clock transitions from a 0 to a 1. Before that moment and after that moment, the output is absolutely stable regardless of what the input's doing. But at the moment where the clock changes from 0 to 1, that's when the output can change. and it will take on whatever value the input currently has. So let's look at a timing diagram. So here's our D input, here's our clock, and here's our output Q. And let's suppose Q is low to begin with. D can be high, it can be low, it can be doing all kinds of things. But at the moment when the clock rises, if D is high, the output goes high. And D can continue to change, and the output's just going to stay high. And when the clock drops, D happens to be low, doesn't matter. The output's still going to be high. But then at this next positive edge of the clock, the circuit looks at the D input. The D input is low. Okay, right there, the output's going to go low. So the only thing that matters is this instant in time and this instant in time. Everything here, 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 irrelevant. Right? So an edge-triggered device. The output changes only when the clock transitions, in this case from 0 to 1. Alright, so that's called a flip-flop, and that's the building block of all of our sequential circuits. And this clock, that's the same clock you find in your PC. When you buy a PC and it's got a 3.2 gigahertz tag on it, right, saying this is the clock speed, that's the clock that they're talking about. It's a clock that's driving all of this sequential circuitry. And basically, in between each of these clock ticks, the positive going edges, things can be changing, but they're mostly ignored. That's when the circuitry inside the machine is taking time to adjust to a new state. Inputs are moving through circuits and causing outputs to change, and all of that stuff is happening, and then everything should stabilize by the time the next clock tick happens right here. And now a whole bunch of other things change, and all of that change stabilizes, and then the next clock tick happens. And in a typical PC, there are a lot of different clocks. There's a base clock, might be 3.2 gigahertz, 3.2 billion ticks per second, and that gets divided down to create clocks for different parts of your systems, clocks for your memory, clocks for your I/O, and so on and so forth. But this is basically, what the clock is. All right, so one more thing to talk about here. This is a different type of device that we're going to deal with in this class called a 555 timer. If you're curious, look up the wiki page on the 555. Look at some of the history of it. It's a fascinating history back in the 60s. It's one of the best-selling integrated circuits of all time. It was started as kind of a skunk works project by someone who just thought it would be a cool chip to make. Boss didn't want him to make it, but he went ahead and did it anyway, and it ended up being one of the best-selling chips of all time. So in the textbook, there's a section in Chapter 3, Beyond Standard Logic. This talks about the 555 timer. It's a timing chip that can do a number of different things. The way we're going to use it is what's called an astable configuration. It's a setup where it will generate pulses. Its output will change between high and low over and over and over again. But you can do a lot of things with this. You can make it generate a single pulse. You can make it look at an incoming set of pulses, and if a pulse is missing, have it generate an output. And you can buy, entire books that just show you different circuits you can build with this. There's competitions every year to see who comes up with the most creative circuit using this. You can buy this on t-shirts, all kinds of things. All right, so here's the configuration we're going to use, and it's a little tricky to wire up, but it's a good exercise in Tinkercad. U1, that's the 555 timer. We connect ground to pin 1 and power to pin 8. Right, it's an 8-pin device, so ground goes here, power goes there. The rest of it gets wired up according to this diagram. So pins 2 and 6 get connected together. Pin 2 and 7 get connected through a resistor that we're just calling R subscript B. 7 and 8 get connected through another resistor, RA. Pin 2 gets connected to ground through something called capacitor. This is a different kind of device. They're like resistors. They have two leads on them, but they look different. They're usually little tiny brown discs with two wires coming off the bottom. And they don't have any direct connection from one lead to the other. But if the voltage across here starts changing, it starts to allow a little bit of current to flow. So they're a really fun device. If you're a double E student, you'll do a lot of design with capacitors when you start working with filters and oscillators and so on. For us, we're just going to take a capacitor, connect between pin 2 and ground. And then pin 4 gets connected to pin 8. That's the reset line. It's got a bubble on it. So if we put a 0 in here, the circuit gets reset, nothing happens. So we want to connect this directly to 5 volts, right, through connected to pin 8. And then we put this little tiny capacitor, 0.01 microfarads, farads are units of capacitance, between power and ground. Again, it's not going to create a short because inside a capacitor there's no direct connection from one lead to another. There's a little air gap. But as voltage between here and here starts to change, we get a little bit of current flow. This is called a despiking capacitor. All right, and then pin 8 and 3 we connect through a 1 kilo ohm resistor. And then we take our output on pin 3. And what this circuit does is it oscillates. It outputs 5 volts, 0 volts, 5 volts, 0 volts, 5 volts, 0 volts, forever. And the question is, how long does the output stay high? And how long does the output stay low? And so this is called T subscript H, and this is T subscript L. And by controlling these, we can make a lot of different changes to this waveform. For example, if we made this half a millisecond and made this half a millisecond, we would be going up and down a total of 1 time every millisecond. That's a 1,000 hertz, 1,000 cycle oscillation. That's an audible tone, right? It's about 1 octave above a tuning A440, and it would sound like a buzzy kind of sound because it's a square wave. It's got lots of harmonics. We hear lots of higher frequencies in there, and so on and so forth. If we made this a tenth of a millisecond and 9/10 of a millisecond, it would still be going up and down 1,000 times a second, but it would sound different. It would have a different, what we call duty cycle, where it's mostly low, but every millisecond it goes high for just a little bit. And it would be a fainter sound. So in 270, we talk about this. This is called pulse width modulation. We could make this, high for 1 second and low for 1 second, and then it wouldn't be audible if we hooked it up to a speaker. But if we hooked it up to an LED, we see the LED turn on and off once every 2 seconds. So how do we know what this is going to do? Well, there's some formulas, right? Depending on the value of RA, RB, and C, we can use this formula. 0.693 times RA plus RB times C, that's how long it's high. And 0.693 RBC, that's how long it's low. And this is for, ohms and farads. So a mega ohm is 1,000,000 ohms. A microfarad is 1,000,000th of a farad. So if this is 1 meg, and 1,000,000th, this is 2 million times 1,000,000th. This is about 2. Time high is going to be about 1.4 seconds. And time low is going to be about 0.7. So if we hook an LED up to this circuit with these values for the resistors and the capacitor C, and we put an LED on here, we'll be able to observe it oscillating. And this is part of what you'll do in one of the labs where we wire up a 555 to make this simple oscillator. And eventually we'll use that oscillator to control our traffic intersection and use that for changing lights from green to yellow to red in a controlled way. All right, so that's the 555 timer. We'll be playing more with that in upcoming labs. So next time I want to dig further into the idea of these flip-flops, look at how we describe them, something like a truth table, but a transition table. Look at some of the real-world characteristics of these flip-flops, different types of flip-flops, and then start to see some of the things we can do with them. And then next week, this will take us into starting a discussion about state machines. All right, see you next time.